Hello, thank you for seeking my presentation. I'm Wayne Strasser, and I'll be describing today simple feed inversion transforming a slurry atomizer. By way of a brief introduction, I'm going to outline what we're trying to accomplish. Should be no surprise that waste treatment is a hot topic, and industrial wastewater treatment sludge, WTS, is present in many industries. Should we choose to dispose of this, in many situations it would be considered a wasted energy content. And with landfills reaching capacity and increasing populations, the locations for disposal of that wastewater treatment sludge should be lessening. Again, it should be no surprise that energy demands are another hot topic. With scarcity of resources, and we're always needing alternatives to conventional energy production. So this brings us to our main opportunity, industrial waste being used and converted to some form that would be a useful energy. This simultaneously addresses major global issues of both waste management and alternative energy production. Our solution to addressing these problems comes in the form of direct spray injection of highly concentrated wastewater treatment sludge into boilers for combustion. The advantages of this would include reduced water usage because we don't have to dilute the sludge to transport it from one location to the next, reduce fossil fuel emissions associated with that transporting, and then obviously, as we discussed, we're simultaneously solving global issues, but it's critical that we have effective atomization, which would be small droplets of this highly viscous wastewater treatment sludge. That would imply a high surface area to volume ratio for drying and combustion once these droplets were in an incinerator, say for example. But it's very difficult because the high viscosity of wastewater treatment sludge creates a large pressure drop, which restricts the flow and will result in poor atomization or larger droplets. The author has a long history of compressible non-Newtonian atomization studies, so we are well suited to attack this problem. Before we can discuss the objectives of this study, we must disclose the disadvantage of this technology. The main issue is that steam is needed to preheat and accelerate the sludge for efficient atomization in our air blast atomizer. However, the steam reduces boiler efficiency because we've already put the latent heat into water to produce the steam, and the steam is going to dilute the combustion reactants. So therefore, our goals are to use a complete atomizer model to establish boundary conditions to a surrogate model downstream of that complete model for atomization study, and to evaluate atomization at full steam flow and then much lower steam flow so that we can mitigate this boiler efficiency loss that we discussed. And then we look for an alternative design to this atomizer, assuming the current atomizer design will not work well at efficient atomization at preferred steam flows. While it is not unusual to atomize biofuels for combustion scenarios, it is unusual to atomize such high viscosity biofuels. This plot shows log of the shear rate on the abscissa and log of the viscosity on the ordinate. Our wastewater treatment sludge are the black dots across the top of the page with a linear fit showing the very high viscosity versus shear rate. It's shear thinning as you would expect for our wastewater treatment sludge. The reference line, the dotted line at about approximately -3, is a reference line from algae oil from a study at reference 1. We see that across the entire range of plotted shear rates, the wastewater treatment sludge is many orders of magnitude higher viscosity than the reference algae oil. I'll illustrate here what we're calling our complete model. This is a half model shown where the steam enters on the left in the vertical pipe, approximately vertical pipeline, enters the annular region and travels parallel to the sludge along the axis of the atomizer, and then the mixture leaves on the right. This particular mesh has about 3 million cells, most of which are hexahedra, and I'll be discussing more meshes in the future. These TETs were converted to poly within Fluent 19.2. It's important to note that the sludge entry is much longer, where it says WTS is much longer than what's shown on the right. And I've clipped it off for illustration purposes, but it does travel the entire length of the atomizer. And what's also important to note is the blue zigzag in approximately the center of the page, illustrating that 1 meter of length has been cut out of the atomizer design just for, again, for visual purposes. I'll outline here the boundary conditions used in the study, and specifically I've called this preliminary because it represents the full steam flow case. And for that full steam flow case, steam is provided at a total pressure of 860 kPa and 177 Celsius to the T connection shown in the previous slide. Sludge is fed as a mass flow boundary at 0.79 kilograms a second, all at approximately 30 C. The important length scales in meters are as follows. The steam inlet is about 0.031. The wastewater treatment sludge pipe is an inch Schedule 40 with an inner diameter of 0.027. The gap between the annular steam flow, inner and outer diameters, is 0.0037, and the outermost orifice diameter on the far right hand of the previous slide is 0.03 meters. The resulting gas-liquid momentum ratio, M, is 0.47. All exterior walls are treated as adiabatic. The steel wall of the sludge pipe that's between the sludge and the steam is allowed to conduct heat, and the outlet to the right of the model was set to a pressure outlet at approximately atmospheric to mimic the pressure inside of our boiler. The solution method will be outlined as follows. We begin with the compressible Navier-Stokes equations as our foundation. Those are well known and not repeated here. Fluent 19.2 is used with discretization schemes as follows. Presto for pressure, upwind bias second order differencing for momentum, upwind bias first order differencing for turbulence quantities and time, piecewise linear interfacial construction or PLIC for volume of fluid interface, at time step size on the order of 10 to the negative 7th. The standard K-omega linear eddy viscosity model is used. While that model is far from perfect, it proves useful for this study. The ideal gas equation of state along with the Redlich-Kwong are both considered for our compressible gas. And lastly, we ignore the effects of surface tension because our Weber number is on the order of 10 to the 6th. A typical instantaneous snapshot of Mach number on our full steam flow case is shown here in this slide, where the colors range from 0 is blue to red is 1 or anything greater than 1. It's obvious that the steam reaches Mach 1 as it leaves the annular tip and begins to meet the sludge, and then as the sludge occupies some of the cross-sectional area that the steam has to share, steam begins to accelerate further, again reaching levels well above Mach 1. Now we truncate the model shown in the previous few slides and cut out most of the steam inlet and focus on the atomization region with a much higher mesh count. The steam inlet conditions in all three dimensions, x, y, and z, are fed to the left-hand side of this slide as shown, and we feed their velocity, pressure, temperature, and turbulence quantities from our other model. This model has 17 million elements, and we're only studying 1/32nd of an azimuth with a base element size of 1.2 e-4 meters in all three directions, right there where the sludge meets the steam. And then just downstream of that, we do a once refinement to halve the element size in all three dimensions to an element size of 6 e-5 meters. And then downstream of that, we refine it again, cutting the mesh element length scale in all three dimensions in half to a mesh element size of approximately 3 e-5. Shown on this slide is an animation from the CFD studies at full steam flow, where green represents the interface between the liquid and the gas. The variable speed in the video is a result of variable time stepping in the solver, and I apologize for the confusion. What we see is this high-speed peeling of droplets off of the interface of the wastewater treatment sludge due to the high-velocity gas passing close to it. Not shown on this slide is the solder mean diameter versus distance from the nozzle, and we see a log linear trend down to a solder mean diameter of about 0.08 millimeters. Now the two downsides to this result is first that we see a nice azimuthal dependence where there's a 1/32nd repeatability in the droplets and the interfacial instabilities. That indicates that our model depends on the azimuthal repeatability. That means there's inaccuracies incorporated in the model, and that's been addressed in my prior studies, and it is a downside to this model. Secondly, not shown here is the droplet size dependent on mesh size, which is well documented in the literature. Both of those are discussed more in the paper. And again, the goal here is just to get a preliminary droplet size, and we say that it's about 0.08 millimeters. This animation, however, shows what happens if we cut the steam flow to 1/10 of the full steam flow used in our stock studies. Again, the green represents the interface between the sludge and the high-speed steam, and the variable speed of the video is indicative of the variable time-stepping routine in the solver. We see, again, high-speed droplet peeling off the interface between the two. We also see some backflow about halfway across the spans of atomization. This droplet size, however, is about 2 orders larger than that of the high-speed flow, of the full steam flow, and the solder mean droplet diameter gets to about 6 millimeters. And that is a volume average value, and you see there's a huge range of droplet sizes here, with a mostly uninterrupted core, followed by peeling off the outer edge. So we showed that the droplet size increased by about 2 orders as we reduced the steam flow to something we would much more prefer. So we introduced this concept of feed inversion, and that is our silver bullet for getting better atomization. This animation shows what happened when we invert the slurry to the outside and put the steam on the inside. So now slurry's in the annulus and steam's in the central pipe. Again, the green marks the interface between the slurry and the gas. Instead of now a high-speed peeling across the exterior of the sludge, we see a peeling off of the interior because that's where the high-speed gas is housed. Now, the flow regime is very different. We see a radial and axial bursting event in between the high-speed peeling events. So we have a much more uniform distribution of droplets because they are blasting in segments. So the droplet size gets down about an order from where it was at the normal feed design. Instead of 6 millimeters, it's down to about 0.5 millimeters. Now 1/20th of the normal steam flow, this is 1/10 in this animation, but 1/20th was also considered. It's not shown, and it shows a very similar regime, and it levels out at approximately 0.6 millimeters of solder mean diameter. As often occurs in real life, when one door opens, another one shuts. We discovered that when we move the steam to the central pipe and the sludge to the annulus, which has much less flow area, the slurry pressure drop was unacceptable. So we propose 3 new annular cross sections, all larger than the first one, shown in the bottom symmetrical meshes. The one on the far left is 0.0071 annular size. The one in the center has a 0.0098 sludge diameter or thickness. And then the one on the far right has a 0.012 meter sludge thickness. You see, moving from left to right, that as the annular region of the sludge changes, so does the available steam pipe size we can insert in the center. The reason this occurs is because the overall dimensions of the atomizer were fixed to fit into the industrial boiler. And as a result of that, the gas-liquid momentum ratios among those three are 3.7, 18, and 60. So the question is, which is going to win? The fact that the annular sheet is thinner, or the fact that there's higher shear on the central pipe of the steam when that annular sheet gets thicker? You see that they cannot be independently adjusted. As we thin the annular sheet, we also had less steam shear and vice versa. This animation illustrates what occurs when the sludge annulus is the smallest of the 3 that we tried in this new batch of cases. This is with 1/20th of steam flow, and again, the variable speed of the video is indicative of the variable speed time stepping in the solver. You see a much more uniform distribution of droplets than we've had to date, and our new solder mean diameter at the very end of the domain is approximately 3 millimeters, which is close to the original low-flow steam result, which is disappointing, but we do have a better distribution of droplets. One thing I set forth to accomplish in the paper was to consider the effect of various metrics by moving the steam pipe diameter and the sludge annular thickness from values of high to low. On this plot, we see steam pipe diameter on the abscissa, and we see sludge differential pressure coefficient of variance on the ordinate. What we're measuring is the sludge differential pressure changing in time. So COV is the temporal standard deviation divided by the mean. Toward the left side of this plot, we see, generally speaking, high gas shear, high sludge layer thickness, high gas liquid momentum ratio, and low sludge internal shear. Whereas on the right side of this plot, directionally speaking, we see a low gas liquid shear, low sludge layer thickness, low gas liquid momentum ratio, and high sludge internal shear. Although there are 3 data points and only 3, I do have a correlation. I call this a correlation. I do have a fit with the power law of R squared of 1. What we're trying to illustrate is the effect of that competition between sludge layer thickness and steam shear, and how that affects the sludge pulsing. So we see that the combination of low shear and low sludge layer thickness produces fewer pressure waves that travel back up the sludge feed passage to the mass flow inlet. Now, with this design, we see that on the right-hand side of this page, droplets are also slightly smaller, but there's no real correlation because there's not enough variation to draw a correlation. In conclusion, I carried out a relatively coarse mesh atomization study for the purpose of improving energy conversion. I found that lower assisting gas flows degraded atomization. I expected that. Inverting the gas and liquid feeds, however, dramatically improved atomization at the low steam flows we sought. The resulting pressure drop on the slurry side, however, that penalty could be mitigated by larger steam annuli. The thinnest sheet, that is the slurry annular sheet, and the slowest steam, which would produce the lowest gas-liquid momentum ratio, produce slightly smaller droplets than other designs, and much easier pressure control. The droplet size, however, returned to its higher level, what we didn't want, if the assisting gas is kept down to 1/20th of the original flow. That may need to be increased some should we want to have high-quality atomization in our steam boiler. What we found was that this new design produced a much better slurry droplet size distribution, but that is currently not measured in our CFD study. We want to do so in the future. Here are 3 references for your consideration. There are more in my paper. I encourage you to review that. I'd also like to bring your attention to the last item on this slide is a paper that Daniel Wilson and I are presenting at this conference that considers P&ID control for smart atomization, and what we're trying to accomplish is maintain atomization quality in times of a highly variable sludge viscosity. Thank you for your time.